what we are doing while applying ANN algorithm, we updated the weights. We updated the different weights. While updating different weights, finally what we are doing while updating weights, finally I want to store those weights. I want to store the optimum weights. To store that model, finally I am applying, I am storing all those features. I want to store the specific model and I want to store all those models. So for that purpose, I created, I generated .h5 file. The purpose of generating .h5 file is this. That is, so if you generate a mod, so if you want to store those optimal weights, to store those optimal weight, we need to generate h5 file. Whenever you download that h5 file, all the updated weights will be present on that specific h5 file. All the updated weight should be present on that h5 file. So whenever you want to run next time that algorithm, you can directly run that h5 file. So whenever you want to train the machine, directly you can run that h5 file and you can obtain the result. That is the purpose of that h5 file. In today's class, we will discuss regarding convolutional neural networks. So coming to this convolutional neural networks, I already forwarded you the video. So in your WhatsApp group, I will forwarded you all the videos corresponding to convolutional neural networks. The major purpose of this convolutional neural networks is the image processing, image detection kind of problems, image recognition kind of problem. Whenever you want to work on images, we need to aware of this convolutional neural networks. So here, so before this thing, you need to understand why we are going to this convolutional network. So here, coming to deep learning, first thing is here we are taking help of human brain working. So how human neural network system works. Based on that thing only, we are developed the deep learning application. Out of this, here coming to image detection also same thing happens. What happens? So we have a brain. With the brain, we connected different neurons will be connected to that brain. So whenever you see the image, what happens? You capture all the features of that image. Then in your brain, below your brain, we have different neurons. At that level, all these images pre-processed. After pre-processing that, we can recognize that specific object or that specific image. So here, how to implement this entire process in the machine? How to do the same all steps with the machine? How machine can understand this kind of information? We will discuss that thing in today's session. So first we will see the intuition behind this thing, why we need to learn these convolutional neural networks, what is the background of this thing.
Hello and welcome back to the course on deep learning. Depending on the features adjust, if you look to the right side of the image, just look at the right border of the image, you'll see a person looking to the right. If you look at the left border of the image, you'll see a person looking at you. And this just proves that what our brain is looking for when we see things is features. Depending on the features that it sees, depending on the features that you process, you categorize things in certain ways. So when you look on the right side of the image, you see certain features of a person looking to the right because they're closer to your center of focus. And therefore, your brain classifies it as a person looking to the right. When you look to the left side of the image, you see more features of a person looking at you. And therefore, your brain classifies it as such. So let's have a look at another one. This is a very famous image. You probably have already seen it, but what do you see here? So some people will say that they see a young lady wearing a dress looking away. Some people will say they see an old lady wearing a scarf on her head looking down. So I'm going to point these features out and you'll see that it'll become very obvious. So this is the face of the young lady looking away. She's looking into the distance. That's her coat, that's her hair, that's her little feather in her hair. And on the other hand, this is the head of the old lady looking down. That's her nose, that's her mouth, that's her chin, that's the scarf on her head, and she's looking down. So as you can see, 2 in 1, and depending on which features your brain picks up, it will switch between classifying the image as one or the other. The oldest one of these illusions recorded in the printed work is this one. It's the duck or the rabbit. So is this a duck or is this a rabbit? Another example. And now I'm going to show you an image which will just, for a second, just look at it and see what emotions or what kind of experience, visual experience you go through. So what do you see? Do you feel like a bit, not dizzy, but a bit dazzled? Like your brain is trying to understand what it is. Like it's jumping between her eyes, the up and down eyes. And it's a classic example of when there are certain features where it could be this, it could be that, but your brain cannot decide. And because both seem plausible. And so basically all of these examples illustrate to us how the brain works, that it processes certain features on an image or on whatever you see in real life, and it classifies that as such. And you've probably been in situations when you look over your shoulder quickly and you see something, you think it's, I don't know, if it's like a ball, but it turns out to be a cat, or you think it's a car, but it turns out to be a shadow, and things like that. That's because you don't have enough time to process those features, or you don't have enough features to classify things as such. And this is, for me, this is very interesting, because what we're going to be doing with neural networks, with convolutional neural networks, is very similar. And you'll find that the way that computers are going to be processing images is going to be extremely similar to the way we are processing images. So it's very valuable to understand and just kind of remember these things, that this is how we do it. And I'm going to take this lady off your screens because she's probably already freaking you out by now. So here's something different. Here's an experiment. An experiment done on computers, on convolutional neural networks. So we're slowly moving now from humans to computers. And this slide is from a talk by Jeffrey Hinton. And here you have, basically it describes an experiment that he had done on some convolutional neural networks that he had trained up. So here you see 3 images, and we're going to go through them left to right and see how you would classify them, and then see how the computer classified them. So on the left, what do you think this is? You probably said cheetah, and you will be right, and this is what the computer said. So, and right away, right off the bat, we're going to learn how to read these images, because if you're going to go deep into convolutional neural networks, no pun intended, if you're going to start learning more and more about them and using them, you'll see a lot of these. So, and I've actually seen people read them incorrectly. So here at the top, cheetah is what it actually is. So that's the actual correct label of the image. That's what the label of the image is, regardless of any processing and computer vision. And then here are the guesses, the top 4 or 5 sometimes guesses of the algorithm, and they're given the probability. So the computer said, or the neural network said, cheetah, leopard, snow leopard, or Egyptian cat can be one of the 4, and cheetah has the highest vote. And throughout this part of the course, you will understand what these votes mean and how they are derived. But for now, it's pretty intuitive, right? So it's a cheetah in reality, and the neural network guessed right. It said with a high probability, about like 95, 99%, it's a cheetah. Then the second one, what do you think that is? That is a bullet train. And the neural network was able to distinguish between bullet train, passenger car, subway train, electric locomotive. Those are the top choices. Of course, it had many more options. These neural networks learn to distinguish from not just 4 categories, from dozens, thousands of categories at the same time. So those are the 4 options that it picked. And so that's bullet train, and it's bullet train. So what do you think the last one is? There are a couple of options, right? It's not very clear what it is. It could be a frying pan, it could be a magnifying glass, it could be even maybe a pair of scissors, some might say. Well, the neural network said it was a pair of scissors. But you can see how you can go wrong here. First of all, it's not a very clear image, and also you can see that the probabilities are not as clear here. So the neural network was a bit confused, a bit indecisive, just as we are. So it said scissors.
So don't worry, by observing at these images. So here he is explaining the performance of the convolutional neural networks. So if you work on image detection problem, how these convolutional neural networks are working and how much accuracy we are getting by by checking the performance of the convolutional neural networks on these images. So here we are getting
This
very
is
good
much for
accuracy. That's
building.
why these are the suggestible approaches to proceed with the neural networks. So here, whenever we want to work on image detection kind of problem, these are giving very good accuracy. Then he is suggesting us to use convolutional neural networks for image detection kind of problems.
Network. So a massive increase, and they're just going to keep going that way because it is a very important field. That is where all the things happen, such as like self-driving cars. How do they recognize people on the road? How do they recognize stop signs and things like that? How is Facebook able to tag images or people in images, and not only just like remember previously years ago you had to tag people yourself, then it would recognize faces, you had to add the names, and now it just recognizes the faces and adds the names at the same time. Well, that is what convolutional neural networks are capable of. And speaking of Facebook, if Jeffrey Hinton is the godfather of artificial neural networks and deep learning, then Jan LeCun is the grandfather of convolutional neural networks. Jan LeCun is a student of Jeffrey Hinton's, and in fact here you can see them together. And Jeffrey Hinton now is pioneering deep learning at Google. Jan LeCun is the director of Facebook Artificial Intelligence Research and also a professor at NYU. So slowly I love this part of the course. Slowly we're building up this these names, or this kind of picture of the profiles of the people who are driving this field. And in the next couple of parts, we'll get to know about a few more, and we'll have this whole mafia, as they call themselves, or Jan LeCun calls them, mafia or conspiracy of deep learning, and you'll learn a bit more about how this whole field developed. And these are just some great people. And so Jan LeCun back in the 80s and the 90s made significant contributions to the field of convolutional neural networks, and as we'll see throughout this course, has been able to develop or help the world develop something so extremely powerful. So moving on to how convolutional neural networks work. You have an input. It's very simple. It's very straightforward. So you have an input image. It goes through the convolutional neural network, and you have an output label. So it classifies that image as something like as a cheetah or a bullet train or something else. Now, kind of like going into a bit more detail, for instance, you can, after a neural network has been trained up on certain images, on certain classified images or categorized images that have been categorized prior, after that you can give it, let's say a neural network has been trained up to recognize facial expressions, emotions. You can give it a face of a smiling person. It's not just a face like a drawing of a face like this, but actual face of a person smiling, and it will tell you that that person is happy. And you can give it a face of a person that's frowning. It will tell you that that person is sad. It can recognize these emotions, and as you can see, that's already very powerful in terms of so many different applications just of this one example you can think of right away. And in both cases it will give you a probability, so it won't say, you know, with 100% the person's happy or sad. It'll be 99 or 98 or maybe 80% when it's unclear of what's going on. And just like we are, right, sometimes we can mistake things for what they're not, or sometimes we can sometimes it's just not clear if the person is smiling or frowning, or if it's a dog or a cat, or if it's a train or a bullet train, right? Sometimes we haven't seen enough features, and it all goes down to features, because that's how we process visual information, as we saw from the start of this tutorial. So, but how is a neural network able to recognize these features? Well, it all starts at the very basic level. Let's say you have an image. You have two images. One is a black and white image of 2 by 2 pixels, and one is a colored image of 2 by 2 pixels. Well, neural networks leverage the fact that the black and white image is a two-dimensional like array. So the way we see it right now on the left is just the visual representation, right? So it's some kind of picture. And for simplicity's sake, it's just a 2x2 picture. But in computer terms, it's actually a two-dimensional array with every single
Sorry. So here, remember one thing, coming to the real-time scenario, what happens means whatever the information we are visualizing, whatever the image we are visualizing, that image will be measured with the in the form of pixels. So here, pixels are nothing but intensity values. Intensity is nothing but information presented the specific grid. So let us assume, so here in this example, he consider 2 cross 2 pixels image. He is taking very simple image. So initially he is considering binary image or grayscale image or black and white image. So if you consider black and white image, so for each and every pixel, there is only one intensity value. That intensity value will be lies in the range of 0 to 255. If that pixel value is above to 127, if one pixel value is above 127, that will be a white pixel. If the pixel intensity is below 127, that will be considered as a black pixel. So here, that is an analogy. So coming to any image, that will be classified in the form of, the machine will understand each and every image in the form of pixels only. So if you consider black and white image, for each and every pixel, we have only one value. So coming to colored image, so if you consider same sized image, here we have three channels. That means for each and every pixel, we have three intensity values. So for RGB, so for all these three colors, we have different intensity values. If you average all these colors intensity values, we will get optimum color from the WIBGR.
one of those pixels having a value between 0 and 255. So that's eight bits of information. 2 to the power of 8 is 256. So therefore the values are from 0 to 255. And that's the intensity of the color. And in this case, the color white. So 0 will be a completely black pixel. 255 will be a completely white pixel. And between them, you have the grayscale range of possible options for this pixel. And based on that information, computers are able to then work with the image. And that's kind of like the starting point, that any image has a digital representation, has a digital form, and those are just basically ones and zeros that form a number 0 to 255 for every single pixel. And that's what the computer works with. It doesn't actually work with colors or anything. It works with the ones and zeros at the end of the day. That's kind of like the foundation of it all. And in a colored image, it's actually a three-dimensional array. You've got blue pixel, you've got a blue layer, a green layer, and a red layer, and that stands for RGB, red, green, blue. And each one of those colors has its own intensity. So basically, a pixel has three values assigned to it. Each one of them is between 0 and 255, and therefore you can find out what this image, what color exactly this pixel is by combining those three values. And again, computers are going to be working with that. So that's the foundation of it all. That's the red channel, the green channel, the blue channel. And finally, let's have a look at for instance, an example, a very trivial example of a smiling face in computer terms. If we just really simplify things, instead of having from 0 to 255, instead of having those values, just so that we can understand things better and really grasp the concepts, we're going to say 0 is white, 1 is black. Right, so we're just going to simplify things to the extreme, and you will see that that image can be represented like that. So the reason why we've brought this up is because we're going to, all of our intuition tutorials, we're going to structure on images like this, which are very simple, but at the same time, then all of those concepts can translate back to the 0 to 256 range of values, and everything applies the same way there. And the steps that we're going to be going through with these images are step number 1, convolution, step number 2, max pooling, step number 3, flattening, and step number 4, full connection. And
sorry. So initially we need to take one image. After taking one image, what we need to do, we need to digitalize that image. Initially, for each and every pixel, we have values in the range of 0 to 255. So based on by keeping threshold, we need to digitalize that pixel values. If the pixel intensity is below 127, we need to consider that pixel as a 0. If the intensity value is above 127, we need to digitalize that pixel as 1. So after performing that thing, we need to perform convolution operation. So here convolution, while performing convolution, we need to apply different filters. So here coming to our core perspective, we can say that thing as a filter, whereas computer coming to computer science domain, they will say this filter as a kernel. So here to define a specific part of the image, like I want to detect the edges, I want to detect the uh, so I want to perform dilation operation, I want to perform erosion operation, I want to recognize some eyes, I want to recognize some nose, such kind of things. So whatever the feature you want to find, for that you need to apply different filter, that is nothing but different kernels. So whenever you apply the filter on this convolution layer to identify the specific feature, here specific feature is nothing but specific portion of the image. So after that, after performing that convolution operation, after detecting all these features, we have image size is little bit bigger. So if you have more pixels in an image, to process all those pixels, it will take more time. To avoid that problem, we need to reduce that image size. So here, to reduce the image size, we need to perform pooling operation. So coming to our EC terminology, pooling is nothing but downsampling. So here, downsampling is nothing but based on our requirement to process the information in faster manner. If we remove some pixels in the specified range, that is called as downsampling. We are reducing the quality of that image. That is called as downsampling. In the max pooling, we are doing downsampling only. Till now, we have image in the form of square matrices. We are having image in the form of square matrices. Whereas, if we want to apply artificial neural networks concept, we need to have data in the form of single layer. So we need to convert that 2D array in the form of single layer. For that purpose, we need to use this flattening layer. So after that, we need to apply artificial neural network system. So here we need to apply this entire data to artificial neural network system. For that purpose, we need to establish full connection. So here, before going to the artificial neural networks, we are processing the image. That those all steps comes under this convolution. So here
I
we will
can
see what
imagine
is
that probably
convolution
none of
in
these
next video.
words mean much to you at the moment, but
So here, initially we will see what is a convolution operation, what we are doing in this convolution operation.
hello and welcome back to the course on Deep. This is the convolution function. I know we try to stay away from mathematics and keep things intuitive, but I couldn't help but share this formula with you because it is so simple. A convolution is basically a combined integration of two functions, and it shows you how one function modifies the other or modifies the shape of the other. And if you've done any signal processing or electrical engineering or a profession where signal processing is required, you would have inevitably come across the convolution function. It is quite popular. Now, once again, we're going to keep the mathematics light or keep them separate. And if you'd like to get into the math behind the convolutional neural networks, a great additional read is Introduction to Convolutional Neural Networks by Jian and Dima. So the details and material we get ones and zeros to simplify things.
Let us assume it is our input image. In this input image, we have these pixels. So here, I want to detect the specific feature from the image. So whenever you want to detect the specific feature, it might be a nose, or let us assume it is a human being image only. So it might be a feature is nothing but it might be a nose, it might be eyes, it might be a contours. Contours are nothing but edges of that specific person. It might be a horizontal edges, it might be a vertical edges. To detect any feature from the image, we need to perform convolution with the filter. So here we have lot of filters in your digital signal processing. You might discuss about different filters. The purpose of filter is to detect the specific feature from the image. To detect the specific feature from the image. So here we need to perform convolution operation between input image as well as filter. So after performing this convolution operation, we will get new matrix.
And you can see the smiley face there. Then we've got a feature detector. So a feature detector is a 3x3 matrix. Does it have to be 3x3? No, it doesn't. AlexNet, I think, uses 7x7. And then some other, one of those other famous ones uses like 5x5 feature detectors. They can be different, but usually you'll see that they are 3x3, and they are, reasons to make them 3x3. So we're going to stick to the convention of having a 3x3 feature detector. Also, the feature detector is called, these are important terms because you might come across them. There are many different terms for the feature detector, but the most common ones are feature detector, or you might hear it being called kernel, or you might hear it being called filter. So in this course, we're going to be using either filter or feature detector interchangeably, but just bear in mind that it has those names. And a convolution operation is signified by an X in a circle, just as you saw in the formulas before. And here what happens is, on an intuitive level, or just to think of it in terms of what is actually happening in the background rather than the mathematics, well, you take this feature detector or filter and you put it on your image like you see on the left. So you cover the, for instance, in this case, the top left corner, the 9 pixels in the top left corner, and you basically multiply each value by each value, so respective values. So the top 0 by the top left value by the top left value, then basically position number 1 1 by position number 1 1, position by number, or 0 1 by 0 1, 0 2 by 0 2, and so on. So just it's element wise multiplication of these matrices, and then you add up the results. So in this case, nothing matches up, so it's always either a 0 by 0 or 0 by a 1, so the result is 0. Here you can see that one of them matched up.
So here you need to remember simple thing. While performing this convolution, keep this entire kernel matrix at this first location. So here, keep this entire matrix at this first location and multiply each and every pixel which is present at the same place, and add up all the points. So whenever you add all these points, you will get this pixel. So whenever, shift one digit to this side, shift one digit to this side, and keep this same matrix at this location. Keep the same matrix at this location and multiply the pixel which is present at the same location. Then you will get this pixel. Like that, you need to perform convolutional operation for each and every pixel, and you need to fill this entire thing. To find this entire thing, the formula will be
the one on the left matched up, and therefore we got a 1. Here, nothing matched up, nothing matched up, nothing matched up. Then we move on to the next row. So, and the step at which we're moving this whole filter is called the stride. So here we have a stride of 1 pixel. So here you can see again something matched up, the bottom right corner matched up. Again, stride, bottom one in the middle matched up. Here, top right one matched up, then nothing matched up. The stride is 1. You can change the stride. You can make it 1, 2, you can make it 3, whatever you like. Conventionally, the one that works well is usually at 2, so that's what people stick to. And we'll talk about what the stride is towards the end of this tutorial. So here we've got, we're matching up, so we just keep going. Oh, here you can see we've got a 2 because 2 of them matched up, and so on, and so on, and so on. There we go. There's
so here simply I'm not doing anything. Simple, we need to take input image pixels. After that, we need to take any feature detector. So here we are detecting one feature. So here we need to keep this entire feature detector at this first location. So in this 3x3 box, we need to keep this 3x3 box, and we need to multiply each and every pixel. The point present at the same location with this kernel digit. So whenever you multiply and add all those digits, you will get first pixel. Like that, you need to keep. So next time we need to shift this thing at the right side. So if you switch this thing to right side, you will get this pixel. So like that, if you switch this digit one more digit right, you will get this pixel. Like that, we will get all these pixels. If you shift this entire matrix to downside here, you will, so if you keep this entire matrix like this here, 3x3 matrix fashion, you will get this pixel. Like that, we need to move this entire matrix in this input image. Then you will get feature map. So here, feature map is nothing but it is a map which is corresponding to any specific feature. So if you are detecting the edges, it will be works as an edge detector. If you are working to detect an ice, it is a works as an eye detecting feature map. Like that, to detect a complete image, we need to perform lot of convolution operation. For one feature, we need to perform this convolution one time. So if you want to take 32 features from the image, if you want to take 64 features from the image, so whatever, how many features you want to take, that many times you need to perform convolution operation with the image.
Sometimes
Remember this
I
thing.
think to myself in the wrong way, but it's the correct. I don't choose that. How come there's many of them?
So here it is a thing. So if you want to capture one feature, here it is a one convolution operation and it is corresponding to one feature map. Whereas if you want to detect lot of features from the image, we need to perform this convolution for many number of times with the different kernels. So here kernel is nothing but feature detector. So here to detect the feature, we need to perform convolution operation with the specific filter. That filter will be called as kernel. We need to detect lot of features from the image. So if you consider human image itself, in the human image, what we need to detect? We need to detect human eyes, we need to detect human nose, lips, as well as hair. So we need to consider a lot of parameters. To process all these features, if to detect all these features, we need to apply this convolution for many number of times. So how many features you want to detect, you need to perform convolution that many times. So here I will forward you the one more session link. Join in the new session so that I will explain you the project also related to the convolutional neural networks. So here,
But we create multiple feature maps because we use different filters, right? And that's another way that we preserve lots of the information. So we don't just have one feature map.